Section 4.1, Systems of Linear Equations. So we have been studying logarithmic models and logarithmic regression and exponential regression and so forth. And now we're actually going to jump back to chapter 4, and really we're going to return to talking about linear functions and linear modeling, but we're going to do it in a more advanced level. So as you can see here, this is systems of linear equations. So rather than just having one linear equation, we're going to be looking at multiple linear equations simultaneously. And here's an example of this. As you can see here, I've just got two linear equations, and this is a system. So it's a system of two linear equations. Now, if you don't recognize these as linear, you need to, well, I guess you need to go back and look at the definition of a linear function, because these definitely are linear. You might be thinking, oh, I thought linear functions looked like this, or something along these lines. Well, I can make either one of these equations look more like this simply by moving the 2x here to the other side and then dividing by 4, or moving the 3x to the other side. So you can move these terms around using just the basic algebraic rules, but you should still recognize that these are linear, right? Okay, and so to solve a system of linear equations, what does this mean? This means to find an xy pair that makes both equations true. So that's all we mean when we say to solve a system of linear equations. Now, graphically, what that would look like, because remember these are lines, so if I graph these, I will have a line. I'd have to, if I wanted to graph them, I could do this. I could take the first one and rewrite it like so. I could rewrite it like negative 2x plus 8, and then this would be divided by 4, and this would be divided by 4. And this one I could rewrite as negative 3x plus 7, and then this would be y1, and this would be y2, and then we could graph these two lines. And so an xy pair that makes both equations true, that's just basically a point. So if this is some line and this is some other line, where they cross one another would be that point that makes both equations true. Okay, so we could certainly solve this graphically by doing by graphing both equations and then doing calc intersect. So that's one method, but we're actually going to be doing this more algebraically. So we're going to discuss a couple of different algebraic methods for this. Actually, before we get any deeper into that, let me run through a few of these slides to make sure we've got all our terminology straight. So I was talking about linear functions. The functions that you see right here are in what's called normal form. So normal is sort of a specific math word. I know you thought you knew what normal meant, but normal in mathematics, we have standard form and normal form. So this is just the nomenclature that we use for this form of a linear function, where the x and the y's are together on one side and the constants on the other side. Okay, and then we could convert this to mx plus b form by moving terms over and dividing, as I've done in this example. Okay. So, and the next slide talks about just solving the system graphically, which I actually had addressed already, but here you can see both of those equations solved for y. So the only difference here is that these fractions are reduced, so that would be 1/2 and that would be 2. Otherwise, these are the same. And then this would be y1, this would be y2, and by graphing these two functions and doing calc intersect, you should find that the xy pair that works for this is the point 2, 1. Okay. Now that's great, and this is a perfectly valid method to use, but there is one big weakness to this. the big weakness to this is that with our technology, with the TI calculators, we cannot do this method of graphing, of solution by graphing, to any linear system that has more than 2 unknowns. So we haven't even looked at any linear system with more than 2 unknowns, so you probably don't know what I'm talking about, but basically just if we have 3 variables, so if you have x plus y plus z equals a constant, 5 or whatever, and then we have other equations like this. This is actually has 3 variables and therefore could kind of exist in 3 dimensions, whereas these are 2-dimensional equations. So our calculators can't graph this. So we can't do a linear solution, or we can't do a graphical solution to any system that has more than 2 unknowns. And having more than 2 unknowns is very common. So this is, even though it may seem sort of like an esoteric thing in the moment, this is not an unusual thing to do. So the graphical linear system method really is only good up to a point. Okay, so we're going to kind of take a hard left here for a little bit and talk about these things called matrices. The plural is matrices. A matrix is a singular, matrices is plural. Eventually we'll get back to talking about the linear system and talk about how we can solve that linear system. But for a little bit, we're going to take a detour. Actually, you know what I think I'm going to do? Sorry to kind of go left and right here, but maybe let me go back and actually just solve this system algebraically, showing you one method. And then we'll come back and we'll talk about the matrices. So I don't want to leave you hanging too much in this. So I know we talked about solving this system graphically, but let me just show you a way to solve this algebraically. So here's a method, which you probably already know. And I'm going to call this the substitution method. Okay, so the substitution method basically is that we solve, let's call this equation 1 and this equation 2, and we can do this in either order, so it doesn't have to be, whatever order I do, I could also do it in the other order, that's all I'm saying. But here's the method. We solve one equation for, it doesn't matter which one, but for either x or y, and plug that in to the other equation. So there's a few more details, but that's it in a nutshell. So let me actually implement this. It won't take long. So let's actually do this for this system. So I could solve this equation number 2 for x or for y, or I could solve equation number 1 for x or for y. Generally do the one that's easiest. So number 2, yeah, I can solve number 2 for y very easily just by saying y equals negative 3x plus 7, right? That's the easiest transformation to make. And now what I'm going to do with the substitution method, let me make this a little bit larger. For the substitution method is I'm going to take this, and this is going to, when I say plug in, I'm going to plug this in for y up here. So that's going to go into equation 1. So now I'm going to go to equation 1, which is 2x plus 4, and instead of putting y right here, I'm going to put in minus 3x plus 7, because that's my expression for y that I got from the other equation. And now notice that you have an expression that only has the variable x, and so we're going to solve this for x. So that would be 2x minus 12x, and then that's 28 equals 8. 2x minus 12x is negative 10x, and then 8 minus 28, that's going to be negative 20. And so we get x is, that's negative 20 over negative 10 is positive 2. So x equals 2. And so now what do we do? To finish the substitution method off, we take the 2 that we've gotten for x and we plug that. So I'll just write it here. So now plug into either equation and solve for y, because we know x, but now we need to get y. So if x is 2, if I put, actually the easiest one is this one because it's already in a nice form. So I can just do y equals -3 times 2 plus 7. That's -6. So 7 minus 6 is 1. So we get y equals 1. And so we get the point is 2, 1. Now remember, that was what we got. Whoops. That was what we got right here. Right when we solved, well, we didn't actually do it, but we talked about solving it graphically. It was 2, 1. So we've now solved it algebraically, one using the substitution method and graphically. Okay, so let me now return to, I was about to get into this subject of matrices. Let me now return to that, and eventually we're going to go through all this stuff about matrices, and you're going to wonder why I'm talking about this, but eventually this will return back to linear equations. So here we go, let's dive in. So a matrix, what is it? Well, it's just a rectangular array of numbers. So it's just numbers arranged in a rectangular fashion. And we have special notation. So we use these little square brackets. That's so you know if I write this that I'm talking about the matrix A. Although it's very easy to forget to write the square brackets, so I'll try not to forget that. But as you can see, this matrix has a total of 6 numbers in it. It has 2 rows and 3 columns. Right, so there's my row 1, there's my row 2, there's column 1, column 2, column 3. This matrix, when we talk about the size or the dimension of the matrix, we're talking about the number of rows and the number of columns. So since we have 2 things to think about, we state the dimension sort of like when you buy like lumber, it's like a 2x4, you know, from Home Depot, so, or Lowe's or something. So we state the rows times the columns. So this has 2 rows and 3 columns. So this is a 2x3 matrix. A 2x3 matrix. That means rows first, then columns. So remember when we're talking about this that the order of when you're stating the dimension, the order is first rows, then columns. Okay. So as I said, 2x3 matrix. The other thing that you need to be able to do is sometimes we actually want to isolate a particular number in the matrix, and a particular number in a particular spot is called an element. And we've got to find a way to navigate around the matrix and identify elements. And so the way we do that is with a double subscript. So that's a double subscript right there. Double subscript. And so the double subscript, A, I, J, that means ith row, jth column. So as you can see right here, A23, that's not A23, it's A row 2 column 3. A is just a symbol for the element. But so row 2, let me erase all this. This is row 2, this is column 3, and so the common thing there is 7. So that element is 7. So A23 is 7. If I wanted to ask you for, say, A12, that's row 1, column 2, that's 4, for example. So this is just the basic navigation of a matrix. Okay, so this is end of this video.